You might have learned about electron configurations in high school, but I still want to run over it with you now just to make sure we're all on the same page. So first of all, what is an electron configuration? Well, it's a notation that we use to describe how electrons are arranged in atomic orbitals. So our goal with this is that you should be able to write an electron configuration for any one of the main group elements in the periodic table. And we're going to use both the periodic table as a guide to this, as well as this kind of picture that's showing the orbital filling order. Before we get too far into that, I first want to briefly review quantum numbers in atomic orbitals. So remember, our four quantum numbers include n, which is the principal quantum number and tells us about the energy of the orbital. And that can range from 1 to infinity. And then the next orbital, or the next quantum number, is L, which tells us about the shape of the atomic orbital. And L can have numerical values that range from n-1 to 0. And in addition to having numerical values, there's also letters that go with those numerical values. So L equals 0 corresponds to an s orbital, L equals 1 is p, 2 is d, 3 is f, and then if we were to keep on with larger values of L, then it starts to follow just the alphabet. And there's also different shapes, like I said, that go with these quantum numbers, these L quantum numbers. And 3 of those, the only 3 that you need to memorize, are shown here. And those happen to be the s, p, and d orbitals. And again, those are the only 3 that you have to memorize. Next quantum number is m sub L. And that gives us the orientation in 3-dimensional space. And also the number of m sub L values gives you the number of that type of orbital. So for example, if I'm talking about L equals 1, my allowed values of m sub L are -1, 0, and 1. Those 3 values correspond to 3 different orbitals of the p type. And so in addition to the one that's shown in my picture up here, which is the pz, I would also have one along the py axis and one along the px axis. And then finally, our last quantum number is m sub s, which doesn't describe the orbital at all, but it instead gives the electron spin, and those values are only plus or minus a half. Okay, so next, let's get into some guidelines for writing electron configurations. And we start with the Pauli exclusion principle that says that no 2 electrons in the same atom can have the same set of 4 quantum numbers. So an example of that would be helium, which has 2 electrons. And so both of those electrons are going to go into the first orbital, or the first stationary state, and that's n equals 1. Within that n equals 1, there's only one type of orbital, the L equals 0. And I know that there's only one of those because there's only one allowed m sub L value. So those 2 electrons have those 3 quantum numbers in common, but then the difference is in their m sub s values. So one of them will have a positive m sub s, the second one will have a negative m sub s. Okay, and that's just what Pauli exclusion principle is talking about. The Aufbau principle, which states that electrons add to orbitals in order of increasing energy, what that means in more detail is that you start filling orbitals at the lowest n value, which is why when I put those first 2 electrons into the helium atom, I started at n equals 1. But then in a n level with more than one L value, you'll fill into the lowest L value first. Or you add electrons to that lowest L value first. So an example of that is that if I happen to be in n equals 2, one of my allowed L values is L equals 1. The other one is L equals 0. So when I fill in electrons in my second level, I start in n equals 2, L equals 0. I fill that up first, and then go into n equals 2, L equals 1. And we'll do examples of this after I get through all of these guidelines that we're following. So the last guideline is Hund's rule, and this says that the lowest energy electron configuration is obtained by singly filling orbitals with electrons with the same spin before pairing up electrons. So I'm going to go back to that p orbital example. So if I'm in n equals 2, one type of orbital that's present there is L equals 1. Those are the p orbitals. And we also know that since m sub L can equal -1, 0, and 1, that means we have 3 p orbitals. And one way I can show those orbitals is by drawing these little boxes. So this would be my 2p orbital set. Each box is an orbital. And you might have done orbital box diagrams like this in high school. If I have 3 electrons in my p orbital, so let's say my configuration ends in 2p3, then by Hund's rule, I would fill in my electrons singly into these p orbitals instead of doing this, where I put 2 in here and then I fill 1 there. Okay, so that's Hund's rule. And again, we'll show more examples of that as we move on in building up these electron configurations. Now to start writing out electron configurations, I want to make a strong connection first to my quantum numbers. So if I think about my picture of the atom in this form, where we used this when we were talking about the Bohr model of the hydrogen atom, we have n equals 1, n equals 2, and so on, 3, 4, and 5. Those n's are our principal quantum numbers. But now we can expand that picture and make it a little bit more detailed. In our n equals 1 level, we have L equals 0, so we know that there's a 1s orbital. And that's the only type of orbital that's possible based on our rules of quantum numbers. But if we go into that n equals 2 level, we know we can have an L of either 0 or 1. So L can equal 0 or 1, which means that I have a 2s orbital for L equals 0 and a 2p orbital for L equals 1. In similar fashion, I can expand my ladder diagram to look like this. And how I'm filling these in is all based on quantum number rules. Oops. And I'm just going to stop there because I am. So that is showing you some of the format to an electron configuration. And this is that diagram that was on the first page of this video. And this diagram gives us the filling order. So this tells us exactly how we follow the Aufbau principle and fill up our orbitals when we're writing out electron configuration. And specifically, if I draw in these diagonal arrows, that's the order that I fill my orbitals in when I'm writing out an electron configuration. So you can see I would go from 1s to 2s to 2p to 3s to 3p and so on. So another way I can show that is by drawing an orbital box diagram again. So if I start with n equals 1, I have a 1s orbital. Then I go to n equals 2, I have my 2s orbital and my 3 2p orbitals. And then I can continue on in 3. I've got a 3s, I've got the 3 p's, and I've also got d's, which there's 5 of those. And just to remind you where those 5 d orbitals are coming from, for d, L equals 2, so m sub L equals minus 2, minus 1, 0, 1, and 2. So there's 5 orbitals. And so again, in this kind of diagram, the boxes represent an orbital. Orbitals can hold 2 electrons. And we're going to show the electrons with arrows. So arrows are used to signify electrons, or to stand in for electrons. So for example, if I want to show 2 electrons in my first orbital, which would be my helium, I would show that like this. So there I followed the Aufbau principle and Pauli exclusion principle. I started in the lowest n level, and I put 2 electrons in there before moving on to the second level, and my 2 electrons have different m sub s values, so their quantum numbers are different. Again, this electron configuration that I've drawn here with these boxes is helium, which has 2 electrons. And this is an orbital box diagram. And that's one way I can show an electron configuration. The other way I would show the same electron configuration, I'll write down here, and that would be, I write it as 1s2. So in that kind of notation, the 1 gives me the n level, or the n value. The letter S gives me the L value. In this case, L equals 0. And then the number, the superscript, is the number of electrons. Okay, so that's the kind of format we're going to use. So let's start writing out some electron configurations. Let's do some examples of electron configurations. We're going to be using the periodic table as a guide. And so I want to review just a couple of highlights of the periodic table. And the first one is that this number up in the corner, which it's sometimes in the corner or sometimes in the middle, that's the atomic number. And that is what signifies what an element is. So that's equal to the number of protons. And in a neutral atom, it's the electrons also. And for the way that I want to show how the periodic table can be used as a guide to making electron configurations, each square is going to represent an electron filling into our configuration. Okay, so if we think about things in that way, then you can see that the periodic table is actually arranged in the order that we're going to write out our electron configurations. And what I mean by that is that these 2 blocks right there represent the S block. So that's the 2 electrons that would go into an S orbital. These 6 boxes represent our P block. So there's 3 p orbitals. Each orbital holds 2 electrons, so that's why there's 6 boxes there. And then this block in here would be our D block. And if we scroll down to the bottom, this block here would be our F block. And again, each box represents an electron. So there's 10 in the D because there's 5 orbitals, each holding 2 electrons. F, there's 14 because there's 7 orbitals holding 2 electrons each. If we're thinking about the periodic table in this way, the n levels are given by the rows in the periodic table. So our first n level is the first row, and so on. This would be the second row, the third row, the fourth row, the fifth row, the sixth row, and the seventh row. Okay? And then, like I said, each of the blocks are going to give us which L value will go into our electron configuration. Another way to show this is sometimes shown in books in this manner, where they take the periodic table and insert the F block into the where it should fit in terms of numbers of electrons. And again, I've labeled the different rows according to the n values, and then you can again see how there would be 2 electrons in an s orbital, 6 electrons in the full set of p, 10 electrons in the full set of d, and 14 electrons in the full set of f. Following the periodic table and going from S to P to D to F is following the filling order that's also given by this kind of diagram, which I started to write earlier in this video. So the orbitals that are shown here are those allowed by quantum number rules. And then the order you add electrons to them is given by the arrows. So that's following the Aufbau principle, where I start at my lowest n level. There's only one type of orbital, so I completely fill in that 1s. Then I go to 2s, then I go to 2p, 3s, 3p, and so on. You can see something weird here happens in that I fill the 4s before I fill the 3d. And again, that seems kind of weird because the 4s level should be higher in energy than the 3d, but you can read the details of that in the book. As we move further away from the nucleus, our orbitals start to get closer and closer together. So I can show you that in a picture. Remember how we drew for hydrogen atom? Here's my first level, here's my second level, but then my third level is closer, my fourth level is closer. Out here at 3 and 4, the orbitals start to overlap. And it turns out that the 4s is actually lower in energy than the 3d. And so that's why there's what seems to be an inconsistency in the filling order, but it's really not an inconsistency. And you can read about that more in your textbook. Another figure that can show the filling order is this one that is showing the periodic table. That's really confusing to me. I really like this kind of picture more, but I also just kind of walk across the periodic table, which is basically what this is showing. So let me show you how I do that on the next slide. Okay, so here's my periodic table again. So just to practice, let's just pick some element, and phosphorus happens to be one of my favorite elements on the periodic table. Ask me sometime why phosphorus is one of my favorite elements. I don't want to share that here. But you can see that it has 15 electrons. So that means that I need to fill those electrons into the available orbitals in the correct order. And I'm going to do that by just walking across the periodic table and filling in an electron into whatever orbitals I walk across. So I'm going to start at the, let me renumber my levels here, 1, 2, 3, 4, 5, 6, 7. So I'm going to start at my n equals 1 and fill in my 1s orbital. So that helium really should be over on the other side. Then I go to my 2s orbital and fill that in. My 2p orbital, I fill that in. My 3s, fill that. And then I start in my 3p and just fill up into 3 electrons full in that p orbital. So that resulting configuration would be 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so let me go over that again real quickly, just with my arrows, just to show you where I got that from. So again, I'm trying to get to phosphorus. So I'm just walking across the periodic table and filling an electron in as I go along. So I'm going to put my helium over here because he really should be there for this to work. And so I go 1s2, 2s2, 2p6, 3s2, 3p6. Excuse me, 3p3. Okay, and that is the electron configuration for phosphorus. Remember that according to Hund's rule, the way that the orbital box diagram looks for this 3p orbital is that each one of those electrons has gone into an individual orbital with the same electron spin. Okay, so now we should be able to pick any element on the periodic table and write out an electron configuration. So let's try another example. This time let's try something in the D block. Let's do iron. So iron has 26 electrons. And so I'm going to have to walk quite a longer distance there on the periodic table. But you write out the configuration as I say it. Okay, and I'll show my path across the periodic table as I am thinking about it. Okay, so we start, we'll put helium there. So we start at our n equals 1, we do 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, but then remembering, thinking back to that diagram with the arrows, this is not the 4d, this is the 3d orbital. So the next part of my configuration would be 3d, 1, 2, 3, 4, 5, 6. Okay, so let's write that out. And you now think about how I got there looking at my arrows on the periodic table. So I filled in 1s2. Oops. For once in a while, the pen kind of has a little freak out there. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So now if I want to mark up my periodic table a little bit more to make it a good guide for doing electron configurations, I'll go to a fresh one over here. And again, remember that each of the rows gives us the n level, or corresponds to the n level. So that's n equals 1, 2, 3, 4, 5, 6, and 7. And then the different rows, as they're combined into blocks, give us the different types of orbitals that we fill in. So this is the S block. This is my P block. And this is my D block. We probably won't do any electron configurations in the F block, but it's down below. And then the only places where the filling order varies from what n level you're in is with the D's. And so let's highlight that by saying that this is actually 3D. That would be 4D, 5D, 6D. But then when we go back into the P's, this is again 4P, 5P, 6P, 7P. And because of the ordering and quantum number rules, the F block, again, is also a little bit different in terms of what n level it's in. So this is actually the 4F and the 5F. And those would fit in after 6S and 7S in order. One more example. So here's my periodic table. I've already got it marked up a little bit. Let's pick something over in the P block. Let's do tellurium, just to be different. So tellurium has a lot of electrons, and so I can already tell that I'm going to get tired of writing out this long configuration. So this is going to give me an opportunity to use an abbreviated electron configuration. So if I were to write all of this out, and let me just walk through it and say it as we go along and put in my arrows, I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. So that's a lot. You'll notice I messed up a little bit when I got to the 5p. I can still write it all out. It's just going to be lengthy and it's going to take a lot of space. So again, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. That's long. So instead of going to those lengths to write out that electron configuration, like I said, I can do an abbreviated electron configuration. And what I do there is, for an abbreviated version, is you go to the noble gas before your element. So in this case, that would be krypton. And you write that configuration in brackets. So let me see if I can extend my page here. So you write that in brackets. And what this does is it signifies that part of the configuration. So that putting krypton into brackets like that substitutes or stands in for 36 electrons. And those are more specifically core electrons. Those are full shells, so those aren't going to take part in the chemistry. And then you add the rest of your configuration just in normal notation. So that would give me everything from krypton out, which would be 5s2, 4d10, 5p6. And those remaining electrons, those are not filled shells, so these are my valence electrons. Okay? And those valence electrons are what are going to take part in chemistry, which is bonding, and that's the next section that we're going to be covering. But that about does it for electron configuration. So I hope you learned something, and if you need to learn more about this, I'm sure there's more detail in the text, and there's lots of practice problems either in the text or the workbook or the lab pal assignments. So thanks for watching.